The document discusses the applications and advancements of resistive plate chambers, RPCs, which are rugged and cost-effective gas detectors widely used in high-energy physics, AP, and astroparticle experiments. RPCs are known for their large pulse heights, reduced cost per unit area, and excellent time resolution, typically around 1 nanosecond. The paper highlights significant progress in the field, particularly with the introduction of the avalanche mode of operation. This mode extends the counting rate capabilities of RPCs to levels around 10 MHz per square centimeter and improves the time resolution for minimum ionizing particles to as low as 50 picoseconds. Additionally, it has enabled the achievement of position resolutions on the order of tens of micrometers, opening up new applications in HEP and even in medical imaging. RPCs have been instrumental in various experiments, such as the Argo experiment at the Yangbajing High Altitude Cosmic Ray Laboratory, the Opera and Monolith Cosmic Ray experiments in Italy, and the ALICE experiment at CERN's Large Hadron Collider, LHC. RPCs are also planned for use in other significant projects like the HARP experiment at CERN and the time-of-flight TOF detector at ALICE. In modern RPC designs, innovations such as the introduction of double-gap structures and multilayer RPCs have improved efficiency, reduced the need for high voltage, and enhanced the detector's versatility. Single-gap and double-gap streamer mode RPCs are widely used in cosmic ray and high-energy experiments, with applications extending to medical imaging. The text also discusses the construction of RPCs, which typically involve a combination of resistive and metallic electrodes, signal-transparent semiconductive layers, and highly isolating layers. These designs enable RPCs to be fine-tuned for various applications, offering a broad range of configurations. In essence, RPCs have evolved significantly since their introduction in 1981, with continuous advancements making them indispensable tools in both scientific research and practical applications like medical imaging. Double-gap designs. Double-gap RPCs, used in experiments like L3 and Bell, are shown in a schematic drawing. These designs involve more layers of gas gaps and pickup electrodes compared to single-gap designs, allowing for more varied and efficient structures. Multi-gap RPCs. A construction method called multi-gap RPC was introduced to enhance the performance of RPCs by including multiple gas gaps without the need for conductive electrodes. This design aims to stabilize the potential across the layers, equalizing the currents flowing in and out by adjusting the gas gain in neighboring gaps. While this method improves the detector's stability, it requires larger voltages and is dominated by the dark counting rate at low ionizing particle fluxes. Hybrid designs. The concept of hybrid RPCs combines metallic and resistive electrodes, retaining the primary property of RPCs, the absence of violent discharges. The key requirement is that no gas gap is delimited by two metallic electrodes. Hybrid designs, like the parallel plate chamber, PPC, are particularly effective in detecting heavy ions, but have limitations in high-energy physics due to the nature of the discharges. Nature of the operation modes. RPCs can operate in two primary modes, avalanche mode and discharge mode. In avalanche mode, the detector responds to ionizing radiation by generating a Townsend avalanche in the gas gap. Discharge mode follows a streamer sequence, where the discharge evolves through several stages. However, the high resistivity of RPC electrodes usually quenches the discharge before it becomes violent. Space charge effect. The space charge effect occurs when a Townsend avalanche creates its own electric field, altering the conditions within the gas gap. The document describes how this effect influences the distribution of the electric field across the avalanche, potentially leading to the development of permanent glow discharge under certain conditions. In summary, these sections describe the advanced designs and complex operational characteristics of RPCs, highlighting how different configurations and modes of operation can be optimized for various experimental needs, particularly in high-energy physics. Efficiency for MIPS. The efficiency of RPCs for detecting MIPs is explored by examining the performance across different gap widths in the avalanche mode. Figure 5 in the document likely shows a survey of results indicating how efficiency changes with varying gas gap thicknesses, with the efficiency typically ranging from 85% to 95% for 2 mm gaps. This efficiency tends to decrease as the gap width decreases, notably showing a significant drop, around 45% for 0.1 millimeters gaps. Counting rate capability. Figure 6 likely presents data on the maximum counting rate of RPCs as a function of the resistivity of the electrodes. The data seems to show that standard high-rate RPCs can achieve counting rates up to 3 kHz per centimeter in avalanche mode and 300 Hz per centimeter in streamer mode. It's noted that specialized designs, such as multi-gap RPCs, offer higher counting rates, particularly for a given electrode resistivity. Gas mixtures. The performance of RPCs in terms of efficiency and counting rate is influenced by the gas mixture used. The document mentions that modern standard RPCs operating in avalanche mode typically use a combination of tetrafluoroethane, C2H2F4, with a small percentage of isobutane, 2 to 5%, and sulfur hexafluoride, SF6, 0.4 to 1%. The addition of SF6, in particular, helps in extending the streamer-free operation region and reducing the amount of charge in the streamer. Background counting rate. The background counting rate of RPCs is a critical parameter, especially when considering the limitations it imposes on detector operations. RPCs can handle relatively large background counting rates without significant adverse effects. However, when these rates exceed a certain threshold, they begin to impact the global rate capability, increase occupancy in the readout electronics, and potentially induce faster aging of the detector components. Table 1, referenced in the document, likely lists the dark count rates for various materials used in RPCs, such as glass, melamine, silicon, and bakelite, and highlights the associated gap widths and counting rates. Notably, 2 millimeter gap streamer mode counters made of glass or bakelite typically exhibit dark counting rates on the order of 1 kHz per meteosquare. This rate can increase significantly with thinner gaps, which leads to higher electric fields. Aging. Aging is a concern in the long-term operation of RPCs, especially in environments with high radiation doses, such as those encountered in high-energy physics experiments. While there is evidence of satisfactory long-term performance in some applications, as demonstrated in the BA-BAR collaboration, the challenges related to aging and the degradation of materials under high doses remain a focus of ongoing research. Time resolution. Time resolution is another crucial parameter for RPCs, particularly in applications requiring precise timing, such as in high-energy physics. Most standard 2 millimeter gap RPCs achieve a time resolution between 1 and 1.5 nanoseconds, ns, regardless of the mode of operation, avalanche or streamer mode. Figure 8 likely provides a comparison of time resolutions across different RPC designs, showing how varying the gas gap affects timing precision. For instance, thin gap timing RPCs can achieve a resolution of about 50 picoseconds, ps. Timing RPCs. Timing RPCs have been developed to achieve extremely high time resolutions, ranging from 50 to 60 picoseconds for electrode areas as large as 9 centimeter squares. These developments allow for very precise time of flight, TOF, measurements, which are crucial in high-energy physics experiments where accurate timing is essential. Figure 9 illustrates the principle of operation for timing RPCs, showing how the initial current grows exponentially until the discriminating level is reached. The timing jitter, which is the variation in the timing accuracy, is shown to depend on avalanche and cluster statistics and is inversely related to the current growth rate. The independence of timing accuracy from the position occupied by the initial charges is a significant feature of these timing RPCs, ensuring that the measurements remain consistent and reliable. Position resolution. The position resolution of RPCs, particularly in standard applications, often focuses on determining the position of the avalanche with an accuracy of about 1 centimeter. This accuracy is usually sufficient for many applications, but improvements are constantly being made to optimize this further. A significant advancement is the use of micro-RPCs, which employ a combination of small gap sizes and precise readout strips to achieve higher position resolution. For instance, a 100 micrometer gap RPC equipped with a solid X-ray converter has shown a position resolution of at least 30 micrometer FWHM in digital counting mode. The precise localization of the primary charge, mainly on the anode, contributes to this enhanced resolution. The diagrams and data in Figure 10 likely support these findings by showing the results obtained from these high-resolution setups. In summary, these developments in timing and micro-RPCs represent significant strides in the field of particle detection, allowing for both high precision in timing and detailed positional accuracy, which are crucial for the advancement of experimental physics and other fields relying on precise measurements. The conclusion and outlook of the paper highlight the broad acceptance and utility of standard resistive plate chambers, RPCs, in high-energy physics, HEP, and astroparticle experiments due to their affordability and effective performance. Despite the potential risk of damaging discharges, RPCs have become a standard tool in the field, offering flexibility in efficiency and time resolution across different modes of operation. Key points include the successful operation of RPCs in both avalanche and streamer modes, with the ability to tune signal charge ranges to suit specific experimental needs. For example, the charge can vary from a few picocoulombs PC in avalanche mode to a few nanocoulombs C in streamer mode. The efficiency of these detectors has reached as high as 99% in some configurations, particularly when using multiple gas gaps, demonstrating their reliability and effectiveness in detecting minimum ionizing particles, MIPs. The paper also notes recent advancements in the development of special configurations of timing RPCs, which have achieved position resolutions as fine as 50 to 70 picoseconds, and opening the door to affordable high granularity time of flight, TOF counters. These RPCs, featuring small gaps, 0.2 to 0.3 millimeters, have proven to be particularly effective for high-resolution applications in experimental physics. Finally, the paper emphasizes the ongoing innovation in the design of RPCs, with exciting developments in specialized applications that promise new capabilities in medical imaging and other fields requiring precise particle detection. The acknowledgement section credits various collaborators and sources of support for the work, and a comprehensive list of references provides additional context and background for the research discussed. These developments signal a promising future for the application of RPCs in high-precision, large-scale experimental setups, offering reliability, affordability, and the flexibility needed to meet the evolving demands of modern science.